Hello everybody, welcome back. In the last class we have started our discussion on the line to ground fault and we have seen some simple circuit equations, their pre-fault conditions and post-fault conditions, and later on we have seen the sequence current conditions as well, right? Now in this class, so we will continue that. We will see what are the sequence voltage conditions and what are the fault currents and the positive sequence currents, circuit breaker rating, all those things we will see in this class. Clear? Now coming to in this class students, now we will see what are the sequence voltage conditions of phase A. Sequence voltage conditions of phase A. Sequence voltage conditions of phase A. Now to see the sequence voltage conditions, just simple thing we are having, the A phase voltage has been grounded, right? The phase A voltage has been grounded. Therefore simply we can write here as VA is equivalent to 0 according to symmetrical networks concept or symmetrical component theory concept. We can write VA can be resolved into 0 sequence component, positive sequence component and negative sequence component which are equivalent to 0, which means that the sum of the voltage components will be equal to 0. So VA0 plus VA1 plus VA2 is equivalent to 0. Clear? So whenever we are having sum of voltage components is equivalent to 0, that fault we can call it as the line to ground fault. For example students, they can give you a question like this. So you can expect a question like this. For example, so this is an example problem. So up to now, so we don't know about the different faults, but here they can that for a fault on a power system network, for a fault on a power system network, we are going to get the voltage components as V positive, the positive sequence voltage is given as J 1.5 per unit, J 1.5 per unit, and V negative is equivalent to minus J 0.5 per unit, and V0 is equivalent to minus J 1.0 per unit, right? By giving this data, they will ask a question like this. Then the fault on the system, will be. So they will give option A as LG fault, option B as LL fault, option C as LLG fault, and option D as triple L faults. Like that they will give the question. Now in this question, now check here, they are given the positive sequence voltage, negative sequence voltage, 0 sequence voltage, and whenever you are adding them you are getting 0. So that as VA1 V positive, VA2 is V negative, and VA0 is 0 sequence is how much it will be? J 1.5 minus J 1.0 minus J 0.5, as it is 0. So then this fault is LG fault. So whenever we are having positive sequence voltage, negative sequence voltage and 0 sequence voltage, all are existed and their sum, whenever you are adding them, whenever their sum is equivalent to 0, then that fault will be LG fault. Like that they will ask the questions, very simple questions only. Clear? Right, that is the sequence voltage conditions of phase A. Now we'll calculate the positive sequence current component of phase A, right? The positive sequence current, whatever the derivations I am writing here. So all the derivations are previous year questions only, right? So each and every derivation is having a relation with the previous year questions, right? The next one we can go for the positive sequence current of phase A. Positive sequence current of phase A. If you see the positive sequence current of phase A, IA1 we need to calculate. To calculate IA1, so as we are having as VA0 plus VA1 plus VA2 is equivalent to 0. So from this one, what is VA0, what is VA1, what is VA2, and from that one we can calculate IA1. So what is VA0? The terminal voltage of the zero sequence network, and VA1 is the terminal voltage of the positive sequence network, and VA2 is the terminal voltage of the negative sequence network. Now if you see here, the positive, negative and zero sequence network, if you draw that one, first of all we will draw the positive sequence network. Positive sequence network, the positive sequence network of the generator, The positive sequence network consisting of the positive sequence impedance and the source, positive sequence source. So here the current flowing is the positive sequence current IA1, and here the impedance is Z1, the positive sequence impedance, and here the EMF is EA1, and here the terminal voltage is VA1, and this VA1 value that you have to write. What is that VA1 value? Please check here, apply KVL in this loop. So this VA1 is nothing but EA1 minus IA1 into Z1. So it will be EA1 minus IA1 into Z1 is the positive sequence network of the generator. And coming to the negative sequence network, students, negative sequence network. In case of the negative sequence network, so we don't have a source, we are having only the negative sequence impedance. The negative sequence impedance only we are having Z2, and negative sequence source will not be existed. EA2 is 0. All these things basics will get in chapter 2 and chapter 3 of the power system analysis. And here we are going to get VA2. The current here it is IA2. So now apply KVL in this loop. So when you apply KVL in this loop, what is that VA2? So VA2 is equivalent to, so as there is no EA2, it will be minus IA2 into Z2. That is the negative sequence terminal voltage. Substitute that negative sequence terminal voltage in VA2 place. And similarly, the zero sequence network, if you draw here, the zero sequence network, coming to the zero sequence network, students, in case of the zero sequence network, the current flowing through the neutral wire will be, the neutral wire of the generator is 3 times of IA0, so that the zero sequence impedance and the zero neutral impedance both you have to write. So this will be the ground point, that will be the ground point. So here you have to write VA0. So this is Z0, the zero sequence impedance, and it will be 3Zn neutral impedance. We know already. So neutral impedance Zn will be replaced with 3Zn. So why? Because the neutral current will be 3Ia0. So to equalize the KCL, so 3Ia0 is the neutral current actually, and Ia0 is the current in one phase. So to equalize 3Ia0 to Ia0, give the 3 to Zn, so that Zn will be replaced with 3Zn. So that you will get 3Zn in place of Zn, and here we will get Z0. Therefore, the current flowing here it will be IA0. IA0. Now what is VA0? So VA0 is equivalent to minus IA0 into Z0 plus 3Zn. Z0 plus 3Zn. And substitute this VA0 value here. So once you substitute all these values, so you will get the positive sequence current, right? Now we'll see, you will substitute that. Just check here. So in place of VA0, it will be minus IA0 into Z0 plus 3Zn plus positive sequence voltage will be EA1 minus IA1 into Z1 plus negative sequence voltage will be minus IA2 into Z2. Minus IA2 into Z2. So these are the things we are having. Now from this one, it is equivalent to 0. It is equivalent to 0. And for line to ground fault, we got the condition that zero sequence current, positive sequence current and negative sequence currents are equal as IA1 is equivalent to IA2 is equivalent to IA3. All the three currents are equal for line to ground fault. Substitute that all are as IA1. Why? Because we need IA1 value. So that by substituting that, so it will be minus IA1 into Z0 plus 3Zn minus IA1 into Z1 minus IA1 into Z2 is equivalent to minus EA1. So that all the minus will become plus, we can write here. So this minus and this minus will become plus. Clear? Therefore, you can take out the value of IA1 outside. Therefore, IA1 outside, you can add all the remaining terms. So it will be Z1 plus Z2 plus Z0 plus 3Zn is equivalent to EA1. EA1, and you can write the value of IA1. So therefore, the value of IA1, therefore, the positive sequence current component IA1 is equivalent to EA1 divided by Z1 plus Z2 plus Z0 plus 3Zn. So that is the value of the positive sequence current. The positive sequence current for line to ground fault. So remember students, this is one of the most important formula. So we are having many questions on this one. So directly they will give the pre-fault voltage as 1 per unit, and positive sequence, negative sequence, zero sequence and different impedances they will give, and you need to calculate the value of IA1 directly. Clear? And once we got the positive sequence current, the denominator of the positive sequence current we can call it as the fault impedance. Now if you calculate that fault impedance here in this equation, so from this equation, so you can call it as the fault impedance or subtransient impedance. Subtransient impedance. The subtransient impedance we can denote it with ZD double dash. So we can denote it with this ZD double dash, right. So the value of ZD double dash is equivalent to the denominator. Add all the things, it will be Z1 plus Z2 plus Z0 plus 3Zn. So that is the value of ZD double dash. Clear? And now we can calculate the fault current for LG fault. Right? What is the fault current for LG fault, students? The fault current for LG fault is fault current. If you check here the fault current formula, IF is equivalent to IA. Is that right? The fault current IF is equivalent to IA only, na? So why? Because it's a line to ground fault. In case of this line to ground fault case, so we have seen already. Check here. So the fault current IF is equivalent to IA only. Clear? Therefore, so we can write in that place. What is IA, students? the value of IA. IA is equivalent to, please check here again. So we have derived one more formula here. Check here. So IA naught is equivalent to IA1 is equivalent to IA2 is equivalent to IA3 in the previous class. Therefore, we can write in place of IA 3 IA naught, 3 IA1, 3 IA2, all the things we can write here. So this is what we have derived in the previous class. Therefore, we can write in place of that one. So this will be equivalent to 3 times of IA0 or 3 times of IA2 or 3 times of IA1. So we know all are same only, na? IA0, IA2, IA1 all are same. And what is the value of IA1, students? Just now we have derived, this is the value of IA1. IA1 divided by Z1 plus Z2 plus Z0 plus 3Zn. Therefore, the fault current IF is equivalent to 3 times of EA1 divided by Z1 plus Z2 plus Z0 plus 3Zn. Z0 plus 3Zn. Right? So try to remember all these values. And this is one of the most important formula, students. So every year in almost all the exams we are having this question, right? So we need to remember this formula. So EA1 3 times of EA1 divided by Z1 plus Z2 plus Z0 plus 3 times of Zn value. So Z1 is positive sequence impedance, Z2 is negative sequence impedance, Z0 is zero sequence impedance, and Zn is the neutral impedance of the alternator. Clear? And once we got all these things, what are the things we got? Voltage conditions, current conditions, impedance conditions. So once we got all these three, we can draw the sequence network for LG fault, which is the most important one. Just check here, students. We can draw the sequence network for LG fault. Just check here, sequence network for LG fault. Sequence network for LG fault. LG fault. In this case, we'll see what are the conditions we are having. The current conditions. The current conditions are IA0 is equivalent to IA1 is equivalent to IA2. So all the three currents are exactly equal. And the voltage conditions are VA0 plus VA1 plus VA2 is equivalent to 0. The sum of the voltage components should be equivalent to 0. And the impedance conditions are ZD double dash is equivalent to Z1 plus Z2 plus Z0 plus 3Zn. So all the impedances you have to add. So we can say that when all the currents are exactly equal, we can write that the sequence network for LG faults are always should be connected in series, right? So that we can write a point here. The sequence network for LG fault should be connected in series. The sequence networks for LG fault should be connected in series. All the networks should be connected in series. So now we'll see how can we connect that. First of all, we are having the positive sequence network. The positive sequence network. So first of all, we'll draw the positive sequence network. So this is the positive sequence network representation. In case of positive sequence network, the impedance here it is Z1, the voltage here it is EA1, the current here it is IA1, and the impedance here it is VA1. Is it right? And the negative sequence network, here I am drawing, it consisting of only the impedance Z2, the current is IA2, and the voltage is VA2. And the zero sequence network, Coming to the zero sequence network, it will be having zero sequence impedance and the neutral impedance. It is Z0 and 3Zn. Z0 and 3Zn. The current here it is IA0 and the voltage here it is VA0. Clear? Right. Now check it. In this case, we are going to connect IA0 is equivalent to IA2 is equivalent to IA1. So which means that all the networks should be joined like this. Should be joined like this. And these are the external terminals of this one. These are the external terminals of that one. What are the voltage here? VA1 plus VA2 plus VA0. So that is the sum. So what is that sum? That sum is equivalent to 0. So voltage sum is equivalent to 0, which means that it should be short circuited. Therefore, we can join this. So where we can write VA0 plus VA1 plus VA2 is equivalent to 0. Is equivalent to 0. So that should be the case. So this network is called as the sequence network for the LG fault. Sequence network for the LG fault. So what is the current flowing here? It will be IA1 or IA2 plus or IA0. All are same only. Right? Analyzing the actual network is same as that of analyzing this network. So this network analysis is very simple compared to that of the analysis of actual network. So that is the theory given by the C.L. Fortescue, the great scientist who has introduced the symmetrical component theory. Right? So the symmetrical component theory is going to give you the simple calculation by analyzing this network. Clear, right? Right. So up to now we have analyzed only by using bolted fault. That means the LG fault whatever you have considered is having a bolted fault. That means between line to ground we are having a dead short circuit fault. In place of dead short circuit fault, students, if you are having any fault which is having some fault impedance, ZF, right? Suppose if a tree is falling on a transmission line, so that we have to consider the impedance of the tree. Why? Because tree impedance is different and conductor, aluminum conductor impedance is different. So we have to consider that impedance also into the case. Therefore, whenever we are having a fault impedance, that means whenever the fault is not a bolted fault, right? When the fault is having an impedance of ZF, fault impedance. So you can write as not a bolted fault or not a dead short circuit fault. In this case, students, right? Yeah. Please check here. We are having the generator. Let me draw the generator. So this is the generator in phase A impedance and phase A source, phase B source and phase B impedance, and phase C source and phase C impedance. Clear? Right. So this is phase B and this is phase C. A phase, B phase, C phase, IA, IB and IC. So initially IA is 0, IB is also 0, IC is also 0. Why? Because the generator is operating under no load condition and the neutral of the generator is grounded through an impedance of Zn. Clear? The current flowing here it is IM. This is EA1 and this will be EB1 and this will be EC1 and this will be the impedances in phase A ZA and here it is ZB and here it is ZC. Like that we are having the impedances. This is the neutral point, students, and this is the ground point. Now check here. On this system on the system, we got a fault. We got a fault. What is that fault? That fault is a unbolted fault, which means that it is having some fault impedance ZF. Therefore, from phase A, you can write as this is phase A. This is phase A where the voltage is VA, and this is phase B where the voltage is VB, and this is phase C where the voltage is VC. Right? Now, if you see the pre-fault conditions before writing the fault, pre-fault conditions as same as that of the previous case, the pre-fault conditions are pre-fault conditions, let me see here. Pre-fault conditions. Please check here, students. Before the fault, when there is no fault in the system, all the three currents are exactly 0, right? Therefore, you can write IA is equivalent to IB is equivalent to IC, all are is equivalent to 0, as there is no fault in the system, Therefore, the neutral current IN is equivalent to 0, and the induced EMFs, the terminal voltage VA is equivalent to EA, and VB is equivalent to EB, and VC is equivalent to EC. So, these are the pre-fault conditions we are having, right? These are the pre-fault conditions we are having. And now on this system, we got a unbolted fault between phase A and ground. So, this is having a fault impedance of ZF, and in this zone the fault current is moving. So, this is the direction of the fault current IF. And whenever the fault occurs, this IA will not be 0 and it is flowing in this direction. This is IA, which is not is equivalent to 0. So, whatever you have written in yellow color here, those are after the fault condition. So, whatever you have written here in the white color are the pre-fault conditions. Clear? So that whenever we are having a fault impedance IF, this VA may not be equivalent to 0 volts. So, previously VA is exactly equivalent to 0, now it is not is equivalent to 0. So, that we have to see the post-fault conditions. In case of the post-fault conditions, please check here, students. What about IA is nothing but IF, both are same, right? IF is exactly equivalent to IA, no change. So, compared to that of the bolted fault, so in unbolted fault condition also fault current is nothing but A phase current. And B phase current and C phase current are 0, IB is 0 and IC is also 0. There is no change in B phase current and C phase current. And what about the voltage? VA is not is equivalent to 0 now. What is the value of VA now? VA is nothing but IF into ZF or IA into ZF. Therefore, the value of VA is nothing but IA into ZF, which is nothing but IF into ZF. This is what we are having in the post-fault conditions. Now we will see the voltage conditions and current conditions. Now check here, first of all, current conditions. The current conditions, sequence current conditions. Please check here, students. The sequence currents are IA0, IA1, IA2. Actually, we cannot get any change. Why? Because as there is no changes in the current conditions after the fault in case of bolted and unbolted case. So, there is no changes, right? So, you cannot get any change here also. We will see that 1, 1, 1, 1 k k square and 1 k square k into IA, IB, IC, right? And we know IB is 0 and IC is also 0. IB is 0 and IC is also 0. Therefore, we can directly write IA0 is equivalent to, therefore, IA0 is equivalent to IA1 is equivalent to IA2. All are exactly equivalent to IA by 3. So, you cannot get any change here. You cannot get any change here compared to that of the bolted fault condition. Bolted fault condition. So, as we do not have any changes in these two conditions, we cannot find any changes in the sequence current conditions also. But if you see the voltage conditions, students, if you see the voltage conditions, we can definitely find some difference, right? What are the sequence voltage condition? The sequence voltage condition will be sequence voltage condition. Sequence voltage condition. Please check here. What is that sequence voltage condition? VA is equivalent to IA into ZF, which is nothing but IF into ZF. IA into ZF or IF into ZF. So, what is that VA? VA is nothing but VA0 plus VA1 plus VA2 is equivalent to IA into ZF. IA into ZF, or which is nothing but IF into ZF. IA into ZF or IF into ZF. Clear everybody? Now we can write in place of VA0, VA1 and VA2, right? What is VA0? The zero sequence terminal voltage. What is VA1? The positive sequence terminal voltage. What is VA2? The negative sequence terminal voltage. So, we can substitute those values there. So, already we have seen in the previous case where we can write those values. What is VA0? It will be minus IA0 into Z0 plus 3Zn. And what is VA1? EA1 minus IA1 into Z1. And what is VA2? Minus IA2 into Z2 is equivalent to IF into ZF. IF into ZF we can write. Clear everybody? Now in this equation we know IA0, IA1, IA2 all are same only. IA1, IA2, IA0 all are same only. Therefore, you can substitute those values there. So, it will be, you can take IA1 outside and you can send all IA1 terms to this side, to current side, and I can send only EA1 this side. Now, it will be EA1 is equivalent to, if you take IA1 outside and you can write Z0 plus 3Zn plus Z1 plus Z2 plus IF into ZF. IF is nothing but IA only, na? What is the value of IA, students? Let's check here. IA is nothing but 3 times of IA1. 3 times of IA1. So, this is nothing but in place of IF, in place of this IF, we can write 3 times of IA1. So, now we can take IA1 here also. So, that in place of ZF, we can write 3 times of ZF. We can write that 3 times of ZF only. Therefore, we can write there, therefore, the value of EA1 is equivalent to, if you take IA1 outside, Z1 plus Z2 plus Z0 plus 3Zn, and in place of ZF, we have to write 3ZF. In place of ZF, we can write 3ZF. Please check here. So, in place of IF, we are writing 3 IA1. Whenever you are taking IA1 outside, you will get 3 times of ZF, right? Therefore, this is the current equation, and from this one, we can write IA1 is equal to EA1 divided by Z1 plus Z2 plus Z0 plus 3Zn plus 3ZF. 3Z. Very simple only. You know? Just check here. Right. Therefore, this is the positive sequence current of phase A with fault impedance ZF. With fault impedance ZF. Clear? And once we got this one, the denominator is nothing but the fault impedance, or not the fault impedance, you can write as subtransient impedance, right? So the subtransient impedance ZD double dash is equivalent to Z1 plus Z2 plus Z0 plus 3Zn plus 3ZF. Like that you can write. So we got the current conditions, impedance conditions and voltage conditions. Now we can write the sequence network condition. So if you see the sequence network, so first of all we have to draw the positive sequence network. So the sequence network we are drawing here, sequence network. First of all we have to draw the positive sequence network. No change, Z1, EA1, the current is IA1 and the voltage is VA1. And we have to draw the negative sequence network and it will be in series with that one. So here I am drawing the negative sequence network consisting of only the negative sequence impedance. The impedance is Z2, the current is IA2 and the voltage is VA2. And we can draw the zero sequence network as well. The zero sequence network of the system, it will be, it consisting of the zero sequence impedance and the neutral impedance. So it will be Z0 and 3Zn, and the current here it is IA0, the voltage here it is VA0. Clear? Right. And as discussed already, these three should be connected in series, right? IA0 is equivalent to IA2 is equivalent to IA1, and these are the terminals outside. And the current flowing here it is IA1, and whenever you are calculating the value of IA1, the impedance should be Z1 plus Z2 plus Z0 plus 3Zn plus 3ZF also should be there, and that ZF should be here. So this is the value of 3ZF. It's not ZF, students. We have to write it as 3ZF. Why? Because the equations are giving you like that, and based on the equations we are drawing the network. Clear? So that the current flowing here it is IA1. The impedance is Z1 plus Z2 plus Z0 plus 3Zn plus 3ZF. So this is the sequence network of the system with fault impedance ZF. For unbolted fault case, this is the network. Clear? Right. Very good. Now we'll see the neutral current of the alternator. The next thing that you have to calculate, here it is. All are previous questions only, whatever I am deriving here. Neutral current or current flowing through the neutral wire. Current flowing through the neutral wire. Current flowing through the neutral wire. Neutral wire. What is the neutral wire current? IN. The neutral wire current IN is equivalent to IA plus IB plus IC. Actually, entering current is equivalent to leaving currents. And we know as the fault is only in the A phase and there is no fault in B phase and C phase, we can write a B phase current is 0 and C phase current is also 0. So we have written already. So that the neutral current is nothing but only the A phase current. So that IN is equivalent to IA, so which is nothing but the fault current. So what is the fault current? The fault current is nothing but, or A phase current is nothing but 3 times of IA1 or 3 times of IA2 or 3 times of IA0. All are same. Clear? Because IA1, IA2, IA0 all are same for LG fault. Therefore, so we can substitute that value. What is that fault current or neutral current? Therefore, the neutral current, which is nothing but the A phase current, which is nothing but the fault current, all are exactly equal, which will be equivalent to 3 times of IA1. What is IA1 value? It will be EA1 divided by Z1 plus Z2 plus Z0 plus 3Zn, and if it is bolted fault, up to this point is sufficient, but if it is not bolted fault, you have to write as 3ZF also, 3ZF also. So these are the all the points that you have to remember and you have to write in case of the unbolted condition. Unbolted condition. Right? So which is the most important formula for unbolted fault case. Clear everybody? Right. So now we got the fault current as well. Now finally, so I will design the system. That means whenever you are having a large power system network, in that large power system network, so whenever you are having an LG fault, how to calculate all these things, right? For that one, we need some generalization technique, right? So we can go for generalization. So finally, I will give you the generalized formula for this one. So generalization. So generalization in the sense we can go for suppose if you are having a generator, so which is feeding a network, so that here we are having some large power system network. Suppose it is network 1, right? And here also we are having one more network 2, right? And here also we are having one more network 3. So like that we are having. So this is the network, right? So in this case, whenever you are having an LG fault, how to give the generalized formula? So in this case, whenever you are having LG fault. In this case, to calculate the LG fault, so you have to apply the Thevenin's theorem. By applying Thevenin's theorem, we have to calculate positive sequence impedance, negative sequence impedance, and zero sequence equivalent impedance of the system, right? So that we can write the fault current in this case, IFLG is nothing but 3 times of the pre-fault voltage, V pre-fault divided by I am writing the values are Z1 equivalent is the Thevenin's equivalent impedance of positive sequence network, plus Z2 equivalent is the Thevenin's equivalent of negative sequence network, and Z0 equivalent is the zero sequence equivalent impedance of the zero sequence network. In this we have to add the neutral impedance also, plus if you are having any the fault impedance 3ZF you have to add. Clear? So neutral impedance should be added in the zero sequence network, right? Z0 equivalent in the sense, so you have to calculate the total equivalent impedance of the zero sequence network, right? Where Z1 equivalent, Z2 equivalent, Z0 equivalent are the Thevenin's equivalent impedance of the positive, negative and zero sequence networks. And sometimes, so they will give the reactance values. So this formula is also approximately equivalent to 3 times of the pre-fault voltage, divided by x1 equivalent plus x2 equivalent plus x0 equivalent plus 3 times of xf. So the impedances are replaced with the reactances. Clear everybody? So these are the all possible formulas what you are having in LG fault, right?